So what does it mean to study algebraic properties of an object like a vector space? This video I want to give a short introduction to what that actually means and what it looks like to help you prepare to work on the first of our activities in this section, 2.1.1. So when I use the word algebraic properties, what I mean is kind of how do our objects that we're studying and the operation that we're trying to study that combines those objects together, how do those interact one with another? So when we're coming up through our math education and learning arithmetic, for example, we first learn about kind of the whole numbers, and then we add negative numbers into the mix, and then from there we do some decimals and fractions and rational numbers, and eventually we get to some real numbers. And so the objects that we're studying are getting more and more sort of generalized in that process. And also the operations that we use, the operations of arithmetic, also get more sophisticated as we study further into mathematics. So the first operations we learn are addition and subtraction. So we learn how to add and subtract whole numbers. And then once we learn that, we broaden it out to multiplication and division. Then we look at exponentiation and radicals. And then we look at transcendental operations like the logarithmic functions and sines and cosines and all this other kind of stuff. So both the objects that we study and the operations that knit them together get more sophisticated as we go along. And an algebraic property sort of just tells us how one of those operations behaves. So here's an example. When we learn addition, right, one of the first things that we learn about addition is that it doesn't matter which order we add two numbers. For any two real numbers x and y, x plus y is the same thing as y plus x. It's called the commutative property of addition for real numbers. And because of that property for real numbers, there is a corresponding property that exists for vectors being points inside of xy space, right, inside of this Euclidean plane, that if they have components x1 and x2 and y1 and y2, because our traditional idea of how to add vectors just has us adding the first components and adding the second components, because that addition is an addition of real numbers, each of those additions is commutative. Right? x1 plus y1 is the same thing as y1 plus x1 as real numbers, and same thing with the second components. And that means that the commutativity that exists for adding real numbers becomes commutativity for addition of vectors, Euclidean vectors, because the components are just real numbers and because the addition is the commutative addition that exists for real numbers. So some of the algebraic properties, like the commutative property of addition, because it's true for real numbers, ends up also being true for vectors. And so we might ask the question, what other properties that we've learned about how real numbers behave with respect to addition, subtraction, multiplication, and division, do those have corresponding properties that also hold for vectors? Or might it not be the case that it's necessarily true for vectors in the same way that it was true for real numbers? And so in this activity, we're going to look at how real numbers, and real numbers for us we're going to denote by lowercase letters like a and b without a little decoration on top of them, and vectors inside of two-dimensional space, which we're going to denote with little arrows on top of them. So keeping scalars, single real numbers, and vectors separate in your mind is important for this activity. And so you want to look at whether each of the properties that's listed here is still going to hold for vectors in the same way that a similar property holds for ordinary real numbers. So what are some of the examples? So one example is this first property that says that if I'm adding three vectors, it doesn't matter if I add the second pair first and add the first one to it, or if I add the first pair first and add the third one to it. This is called the associative property of addition. It holds for real numbers, and then the question is, does it also hold for vectors? Property 2 is also called the commutative property. Property 3, there exists a vector z such that v plus z is equal to v. So there exists a vector that we cannot tell has been added to anything that it adds to, right? It's like whenever we add it to a vector, that vector doesn't change. Does there exist such a vector with that property? This is a property that is called the additive identity property when we see it for real numbers. And for real numbers, the role of this z is played by the real number 0. Property 4 is often called the additive inverse property, that for any vector v, there exists another vector that we call minus v, such that v plus minus v is equal to z, where z is this vector that we were introduced to in part 3. So for real numbers, this is called the additive identity property. It just says that no matter what real number you give me, I can find another real number that when I add them together, the result is my additive identity, in other words, 0. Property number 5 on this list is if two vectors u and v are different from one another, then the only vector that is exactly as far away from u as it is from v is half the sum of u and v, in other words, the average. This is a property that's true among the real numbers. If you give me two real numbers, there's only one real number I can find that is just as far away from one as it is from the other, and that real number is the arithmetic mean, the average of those two real numbers, half of a plus b. So your job in number 5 is to see, is that also true for vectors? 6 is called the associative property again, but here it's an associative property for multiplication. Now, the wrinkle here is that we're only ever going to multiply single real numbers, scalars, by one another. We are not, in general, going to be allowed to multiply a vector by a vector. We can multiply scalar times scalar. We can multiply scalar times vector, but we cannot multiply vector times vector in general. That's not one of the properties that vector spaces are guaranteed to have. Some vector spaces do, but it's not necessary, and so we're not going to take that property for granted. And you'll notice that in this expression for number 6, we're not actually multiplying vector by vector. We're multiplying a scalar times the result of multiplying a scalar by a vector, which is fine. And then on the other side of the equation, we're multiplying a pair of scalars, which we know we can multiply single real numbers together without a problem, and then multiplying a vector by that result. So the question is, are both sides of this equation guaranteed to be the same? Number 7 is a multiplicative identity property. Is it true that 1 times a vector is always going to be equal to that same vector? And then number 8, if you give me any non-zero vector, u, I can find a scalar c such that c times u is equal to some other vector v. This, by the way, is a property that exists for real numbers. If you give me two real numbers, u and v, if they're just single real numbers, and as long as u is not 0, I can find a number that I can multiply u by so that the product is equal to v. That number would just be the quotient of v divided by u. Right? So does this property also hold for vectors? Can I always scale the vector u into the vector v for any pair of vectors u and v that we pick as long as u is non-zero? Property 9 is a distributive property of multiplication over addition. This is true, again, for real numbers, that a times b plus c is the same as a times b plus a times c. And so your question here is it also true if we have vector addition inside of the parentheses instead of addition of real numbers? Is a scalar times the sum of two vectors the same as the sum of that scalar multiple of those two vectors? And then finally, if I add the scalars instead of adding the vectors, if I add the scalars first and then multiply by a vector, is it the same as if I had multiplied the vectors first by that scalar, by those scalars, and then added those vectors at the end of the day? So before you embark on this activity, the last thing that I want to put on your radar screen here is what kind of evidence, what kind of work should you be doing for these problems? So you ultimately want to label these as valid if it's true that any vectors that we could possibly pick, u, v, and w, and any scalars a and b are going to satisfy this equation, or invalid if it's not true. Now, if a property is true, it would be nice to see some explanation for how we know this property is going to be true for every vectors that we pick and for every choice of scalar. And that is the kind of thing that would require us to write a proof in general. On the other hand, for the invalid properties, what I'd like for you to do is to try to show a specific concrete counterexample. Show me a choice of vectors u and v and scalars a and b or whatever, such that the left-hand side of one of these equations is not the same as the right-hand side. Be very concrete and specific with your counterexamples. When you find an invalid example, try to write out a specific illustration, an example, a concrete numbers that show why the property doesn't hold. This is the only activity I would like for us to do in this chapter for now, so that we can save the real good parts that come later on for when we're all back together synchronously in person next week. So this is the only activity for section V1 for today to do with your team.